So hello friends, welcome back to our channel. Now we will continue our last video, that is we are writing the data to EEPROM. In this video we will continue with reading the data from EEPROM. And now how will we achieve whether our data that is read correctly and getting written correctly. So in our last video we have seen that our data is getting correctly written into particular sector from the particular address that we are giving to the function. Okay, so in this video we will check that the data that we have written into particular memory address, we will read that data and we will write it into another page. Right, now here we can see that we have written character E of 64 bytes. So we have written it from 01C0. So from this address we have written our data, right? And as you can see here that there is no data at the 00th location. So what we will do is we will copy this data from address 01C0 to the, let's suppose we will copy it from A0. Okay, so these 64 bytes of data will get copied from AC0 to A0, right? Now we will go back into our function. So you can see that we have our main code, right? This is the same code that we have edited in the last video. Now what we will do is we will go over here and we will enable our EEPROM read function. I will explain the EEPROM read function. Okay, now what we are doing is we are reading EEPROM read, right? We are using this EEPROM read one function. We are reading from the address and we are reading into this pointer. This pointer belongs to 256 bytes that we are reading. So we will go inside this function. Now mem address, the pointer data, and the data size that we want to read. Okay, so let's suppose we want to read only 16 bytes of data, and this 16 bytes of data we will write into A0. This is not predefined. Okay, and let's suppose we will go into their pointer, right? So we have declared the character pointer. It is same as uint 8 pointer, right? So we have declared the character pointer of 256 bytes and we have given the pointer to it. Now what we will do is we want to read the data from AC0, right? And we want to write it from address A0 again. So basically we are reading the data from AC0 and writing it starting from the address A0. So we will modify this code, right? Save it. Once this copy is done, we will go into toggling of the LED function. Now I'll go over here once again. We will see the memory contents. So the memory contents from the address AC0, as you can see, it is 65, right? That is EEEE, and so here it is empty, that is FF. Okay, so this EE 64 bytes only, right? Now 64 bytes of data will get copied onto, oh sorry, we have modified it to 16 bytes only, right? So only 16 bytes will get copied. So 1 2 3 4 5 6 7 8. So this row, only this row will get copied over here. So from from B0 we will see nothing, only at address A0 we will see the the E characters. Okay, so we'll go over here. As our erase function is taking a lot of time, for now we will bypass it. We will save the code. We will build the code, build project. Okay, now we'll go stop here. We'll load the hex file. 347, it is the correct time, 347. Click on open. Okay, go over here and write. We'll need to monitor the EEPROM pins. That's all we need to do, right? Okay, now let's wait for the transaction on the EEPROM pins. Sorry, I2C pins, I2C and EEPROM. So EEPROM is connected through the I2C protocol. And yes, like we are using the GPIO pins, that is we are manually toggling or manually using the GPIO pins uh, to generate our I2C, right? So as you can see, our LED is toggling, and yes, right, the initial contents were FF at the location A0. Now 16 bytes of data has been copied, right? From AC0 it is copied into A0. So yes, EEPROM read function is working properly. Now we will check, we will go over here. Now AC0, we want to modify our data to AC0. Now let's modify to C0. That's fine, that's fine, right? So AC0, right? AC0 from the like, now at AC0 it was E0, right? It was E0. Now what will happen, it will be written as C0 over here. Then C0 will C will be copied, character C will be copied, 16 bytes of character C will be copied over here. Okay, so AC0 and var data 1, size of var data 1. So we are basically whatever the size of whatever it is written into our character array. So we are copying all the data from that array into our EEPROM. We'll save it, right, and we will build the code. Building hex file EEPROM correctly. Load 349. Okay, and quickly monitor it. So at address EC0, character C0 should be written, and after 64 bytes of C character C, E should be written. 64 bytes of E character E should be written, right? And address A0, 16 bytes of character C should be written, right? So as we can see that 64 bytes of character C has been written to AC0 address, and A0 from, like, we are reading from AC0 and we are writing it writing the same data to A0 address. So yes, our code is working perfectly. Now we will go into code. We will try to understand how we have written the read1 EEPROM read1 function, right? Now, like, we have used one flag. This is basically a flag, right? This is basically flag. I'll mention the use of this flag later. Now we want to read this data from EEPROM of data size, right? Whatever length that we are passing, that we want to read this many number of bytes from the EEPROM. So this we are passing in the data size, okay, data size variable. So for that we are using a for loop, right? Now whenever this start condition, right, so basically we will go over here, okay, and I guess let's see, read operations, right? Yep, random read. For read we have to send start condition, then the device address, then read or write, right? First we have to send it write, then acknowledgement, then the memory address, okay? After memory address, once we get the acknowledgement, we don't have to send the stop condition, we have to send start condition again, okay? Then again device address, then read, okay? So we will first concentrate over here, that over here only. First start condition, device address, write operation. So whenever this b stop condition, this flag is set to 0, we'll send a start condition, okay? So in start condition we can, as I have already mentioned in my previous video, we are setting the clock to set. And okay, this is paint. This is the best tool, right? So this is clock, right? This is data, SDA. So let's suppose transition on the data pin. Transition on the data pin should always be when the clock is low, okay? Else it will be considered as a start or stop condition. So for start condition, right, whenever the clock is high, the transition from low to high on data line is considered as a start condition, okay? So here we are setting the clock pin to high, we are resetting, that is we are assuming that the data pin is already high, okay? So from high to low transition on the data pin, when clock pin is high, it is considered as a start condition, and we are setting the clock pin to low, okay? So once this condition is done, we are setting the clock pin to low, okay? So this is our start condition. Now we have sent the start condition. This start condition we have sent, okay? Now we are setting the flag to 1, indicating that we have sent the start condition. We'll again reset it after some time, right? Now we are sending the data write, that is device address with write opcode, okay? So we are sending the device address with write opcode, okay? And in this function we are waiting for acknowledgement, okay, from the EEPROM device. So we are sending the device address, the write with write opcode, okay, write operation. Now we should send the memory address, okay? After this acknowledgement, we are sending the first and second, that is first 8 bits acknowledgement, second 8 bits acknowledgement. So first word, second word address, okay? So we are dividing that 16-bit address into two 8-bit address, okay? Mem address, it is uint 8. So this mem address we are sending first higher bytes, okay? So mem address plus UI, this UI is for multiple sequential reads. We are shifting it to write, that means higher 8 bits will be shifted to like 8 bits only, and lower 8 bits will be not considered, as it will basically make it 0, okay? Then we are giving it to mem address, we are sending it as a first word, higher 8 bits of 16-bit address, okay? Then lower 8 bits of 16-bit address, okay? After that we are simply ending it, like mem address plus UI, we are taking this address, this is a considered address for sequential read, and we are ending with FF. So higher 8 bits will be made as 0, and we are sending that address, okay, over here. So we are completed with start condition, device address with write operation, then first word address and second word address that we have sent. Now we have to send again start condition. Now we have written a repeated start condition. We'll go into this repeated start condition, okay? Now what we are doing is we are setting the data pin to high. We are setting the data pin to high, okay? Because after every clock, after every clock toggle, right, our clock pin, that is SCK pin, will be always low. So we are setting the data pin to high, okay? Then we are setting the clock pin to high. Now there is currently, when the clock pin is high, getting high, there is no transaction on the data pin. Okay. Now high to low transaction on data pin, high to low transaction on data pin, and we are, after the transaction on the data pin, we are making the clock as low. Okay. So this is the repeated start condition, and after each transaction we are giving some delay. Basically this will be some rising delay and all those things. Okay. So this is the repeated start condition. This is the repeated start condition. Again we have to send the device address with read operation. Okay. So device address with read operation, right? This is done, correct? Now we are we are getting the data, we are reading the data. Okay. So device address and then get the data will be available on the I2C pins. Okay. So HAL GPIO write SDA port. Okay. Set pin. Now we have to set this, we have to give the acknowledgement device. Basically data pin we are setting to high. Okay. So we are setting the data pin to high. Now if this has to be set, this has to be pulled up high by the master device. So whenever the slave device, that is our EEPROM device, wants to send a 0, right, it will pull that pin to low. Okay. So that's why we have made this as high. Now we are over here, we are checking over here, if UI plus 1 is equals to data size, right, and mem address plus UI plus 1 is not equals to 128, that is it is not at the page boundary. Okay. It is not equals to 0, then read the data. Okay. With variable 1. Now we will go into this function EEPROM read. Okay. We are sending back, we are returning the 8 bit data, that byte data basically, and we are passing the parameter, that is acknowledgement parameter, which type of acknowledgement we want to send, positive or negative. This has to be provided when reading the data, the acknowledgement has to be provided by the master. So that's why this parameter is, we are passing this parameter. Okay. So uint data bit 16. Okay. Then we are reading the byte data, that's why we have used the for loop for with the 8. Excuse me. So yes, so we are looping, we are using the for loop for 8, right? This condition is for 8 times we will go into the for loop. 8 times we will read the status of the data pin, that is SDA pin. If it is equals to 1, we will write 1 to the data bit. Okay. This is 16 bit, and we will OR it. After ORing, right, we will shift the data bit. So bit by bit we are reading, that's why we are shifting it. Okay. After that, after reading it, we will give the clock. Once all these 8 bits have been read, okay, once all these 8 bits have been read, we are again shifting it to 1. What is happening is, because we are shifting it to 8 times, multiple 8 times, right, our data will be shifted totally 8 times, and that is not intended. Our data should be read, the data pin should be read 8 times, and data should be shifted only 7 times. That's why we are shifting it to write by 1. Okay. So only we are making it by, we are correcting the data basically. Now we want to send the acknowledgement, whether the positive acknowledgement or negative acknowledgement. Okay. If we want to read the sequential data, right, so for that we have to send the positive acknowledgement. And if we want to terminate the data reading, data read operation, we have to send a no acknowledgement with stop condition. Okay, so if the acknowledgement is 1, we are sending the positive acknowledgement. If it is if we want to terminate the terminate reading the data, we are sending the negative acknowledgement and return the data bits. Okay, so this is done. Okay, so now yes, passing this parameter, right? If our data is not equals to data size, means whatever length that we have passed in this function, the number of bytes that we want to read the data, right? Number of bytes of data that we want to read, if it is not matching, right, it is not to the limit, to that limit, right, we are not coming to that limit, then we will send the positive acknowledgement always. If we are coming to the end of reading the data, number of bytes that we want to read, if we are coming to complete that data read operation, then we will send the negative acknowledgement. That's why this condition has been read. Okay, this condition has been introduced. Now we have understood this condition only. What about this condition? If we come to the page end, right, then we want to send the, if we are not at the page end, then we want to send the positive acknowledgement. If we are coming at the page end, then we want to send the negative acknowledgement. Okay, so we are correctly doing that. And if it is at the page end, we are sending the stop condition. Okay, then we are setting this flag as 0, so it will again trigger the start condition. Okay, if complete data has been read, that the number of bytes that we want to read, it is completed, then send a stop condition. Okay, no need to set this flag again. Simply thing. Okay, simple thing. Now I guess we have understood this completely. Okay. Let's go and check. Now first thing we will do is we will modify our code so that, okay, what we will do is from this address we will read data, 16 bytes of data we will read from 1F0, right, 1 2 3 4 5 6 7 8. So from 1F8 we will start to read the data, and we will write it to B0. Okay, so we will modify our code. We will keep it as 0. Read data from 1F8 and write it to B0. Okay, so build the code, go over here, load the hex file, click it OK. Yep. Now as you can see, we started to read data from AF8, right, and we wanted to read only 16 bytes of data, so we'll get 8C and 8E. So if you can see, we are getting 8 C's and 8 E's. Okay, so I hope you understand this video. If you have not understood it well, you can post your questions in the comment section. Okay, few things I want to mention here is we have set to crystal frequency to 8 megahertz because we are using the external crystal, and with the PLL that we are increasing the clock frequency, okay, to maximum so that our simulation gets very fast. So basically we are using the crystal frequency of 8 megahertz. If it is not set in your simulation, set it to 8 megahertz. Okay, then go into design, configure power rails. In ground you can check it should be ground, VSS, VSSA, and the voltage should be 0. For VCC VDD the voltage should be 5 volt, VCC VDD VDDA and VEE the voltage is 0 and there are no nets. Okay, so you should consider all these things, or if you have any questions please comment it, post it in the comment section if you have any questions. If you like my video, if you enjoyed my explanations, please give it a thumbs up or please give it a like, share with your friends, and thanks for watching my video. Have a nice day.